Hello, can you hear me?
Yes, Mr. Quack.
Testing, testing.
Mr. Quack, we can hear you.
Okay, let's begin. How do you all find this worksheet? Manageable?
Yes.
Yes, manageable up to all the way lah. Okay, let's start huh? So today, right, I hope we can do at least half. Okay, why half? Actually, we can go all the way lah, but then I think it's no good because today some of the skills that you learned, I hope you can apply it right in doing the second half. That's why, right, I think half will be quite good. And also, right, the first half is more actually not exactly the first half of gravitation. It actually overlap into the second half, but well, there are more of those orbital type of questions, and also, right, first half is slightly easier. The difficult question, right, I try to push it to the back. Okay, I'm not sure whether I successfully filter out this way. Okay, let's start. So question, the first one, right? Okay, we have a aerial stationary satellite. Okay, so those who have studied, right, they will know that the word in front of the stationary refers to the planet. So why we call it geostationary? Because geo is the name of our Earth. Okay, correct or not? Or geography, yeah, the study of Earth. So geostationary, aerial stationary. So question blah 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 tell you that this satellite, right? What's the surname of this satellite? This satellite's surname is called Musk. Okay, Elon Musk, his son. You see, this is colonizing the planet. Okay, so you see this Elon Musk, right? What they are doing with SpaceX, one day, right, will really become what you see in the sci-fi movies. Or I really think that it will be true, okay, it's just a matter of times, or maybe by 2050, we will see, right, some form of colonization of Mars. And by then, right, you'll be working and you'll be earning some income, okay? And if you have money, right, buy the shares of Elon Musk, SpaceX, okay? Or I haven't buy yet, okay? But I will buy soon, okay? Because one day when they really can colonize a planet, right, they will be super, super rich. So anyway, back to this question. Two characteristics of aerial stationary or whatever stationary satellite. Okay, these are the one. Number one, right, must be same period as the planet itself. Why that? Because, right, the planet is rotating. That's number one, or the planet is rotating. How we know the planet is rotating? Actually, the question I read already, I don't think it actually said, is it? Yeah, it didn't say, but it's have to be one. Otherwise, right, if the planet is not rotating, right, there's no meaning of aerial stationary satellite. You may ask, right, if the planet not rotating, can't you just plant a satellite, right, and let it hover about the same point on Earth all the time? Answer is cannot, or not possible. Why then? Because, right, anything that's hanging above the sky, right, will just fall down, ma. Oh, why is it that moon and satellites, right, they can stay on the spot in the sky, right, without falling? It's because, right, they are performing circular motion. They are actually falling on all the time, or they are experiencing G the same way as we do while I stand here on ground, right? It's experiencing the same G. However, right, it is because these satellites and planets, right, are also, how come my screen share jump out halfway? It's because they are also moving, okay, at a suitable speed tangentially, right, or in a circle tangentially to that part of the circle, such that, right, when they fall, they merely, right, fall into the next point in a circle, okay? So they are originally at part of a circular path, they fall. So falling means what? Falling means you try to drop inwards, what? Or you try to drop closer to the object that's pulling you. But, right, why did it not drop further? It's because, right, you must think, originally on a circular motion, right, you see, let's say this guy, by right, he's supposed to be moving tangentially if there's no force pulling it, okay? And the force that pulls it, right, cause it to fall. So see, instead of going in this tangential path, it actually, right, fall inwards. So it end up landing on the next point in the circular orbit, okay? Then at this point, right, it wants to go tangential again, but it get put in, or it fall inward. So instead of being here, it fall inwards. So it's here. Then, right, you want to go tangentially, but it fall inward, and so on and so forth. That is what gravity, right, is doing to satellite, okay, that allow them to go in circular motion. Well, I believe, right, up to this point, some of you may be still quite confused, right? Why you may be proficient in doing all the mathematics or the gravitational force provides for the centripetal force, but you are not, you may still be unsure, right? Why is that so? And why is it that people say that moon is falling, but it just doesn't come nearer to us? Why is that so? It's because, right, if it were not for gravitational pull, or moon and all satellite would have gone tangentially even further away already. It's because of the gravitational pull. That's why they land back, they fall towards Earth, back onto another point in the circular path. Yeah. So that's a way that you can explain. Yeah, this one is a bit unstable. I mustn't talk too long without moving my screen because it will go blank, right? And then it will jump out. So these 3 points, same period as Mars rotation, same direction of orbit, okay, as that of Mars rotation. Finally, right, this point is some point that some people cannot visualize. Or the orbit, right, must be on equatorial plane. So nobody, right, on any other part of the planet, right, other than on equator, can see geostationary satellite, okay? I'm not correct to say it this way. many people can see, but it will just not be on the same part of the sky, okay, as right, what the person on the equator will see. So the person on the equator, right, will see geostationary satellite, right, all day long. So right above us, right, you look out the window, you see in the sky, right, there's bound to be geostationary satellite already there. It's not saying night time then they appear there and you see the satellite appear in the sky. Oh no, daytime also have. It's just daytime you cannot see. Okay, so that is the thing about geostationary. It's always there, 24/7. Okay, so if you're still not sure, right, go and read the notes. 3 points, right, should all memorize. Okay, because sometimes a question come out is asked for 3, not asked for 2. Next, calculate the mass of Mars. Okay, this, right, you are given already the value for G, okay, which is 3.71. So calculating the mass, right, this is quite straightforward. I put a highlight here. I ask you to memorize. Memorize what? Capital G. Okay. And I also hope, right, that you can memorize a few more number. Memorize, right, but not asking you to use, okay? Because if the question never give, you are not supposed to use. Mass of Earth, okay, is around 6 times 10 to the power of 24. Okay. Radius of Earth is 6.4 times 10 to the power of 6 meter. Okay. Then radius of geostationary, okay, is 7 times radius of Earth. Okay. Why must memorize all this? It's because, right, in exam when you do, you are definitely asked to calculate. You cannot memorize and just regurgitate. But then, right, when you calculate, right, whatever answer that you get, then you can make sense of what you have in your memory, whether this number are close enough or not close at all. If not close at all, right, and seems nonsensical, right, then it is a it's a hint to you to check your calculation whether anything made mistake or not. Okay, next part. This first question is, I feel generally easy for people who are reasonably prepared. Or calculate radius of geostationary. First thing I want to say, right, which is so annoying as I prepare the solution, right, for this set, is, right, every question asked for this, or you must always, every time you use GMM over R square equals to MR omega square MV square over R, in a structured question, you must always write this first line. Okay. This one sometimes no mark one. This line, right, sometimes it's a -1 mark or 0 mark. So if you got right, is no credit. Okay. Never write -1 mark. It's what happened in school exam lah. In A level, you're given a mark for it. School exam 2 nil already, or you simply get deducted. Okay. Don't ask me why. Then, right, here you go on and calculate. So this is an easy one. If you look at the workings, right, they are, I put method 1 and method 2, they are essentially the same thing. It's GMM over R square, GM over R square, I'm sorry, equals to R omega square. Yeah. Because you are given information about the satellite period, or you already know something. At this point, right, there's 2 ways to proceed. One way, right, is to you see, one way, right, is to note that here, this GM, right, you can also, yes, we don't know what is the mass of Mars, although we calculated in the previous part, okay? But what if you are wrong, or what if your calculation is wrong? So there's another way. Instead of using the mass of Mars, which you have found, that is straightforward, or nothing wrong. You can also write, look at here, okay, that G at the surface, right, of the planet equals to GM over R square, where R here refers to the radius of the planet. So this is another identity, right? Sometimes you can use one. So GM is simply equals to G at the surface times R mass square. Okay, so you substitute that in, you can find what is the radius of the satellite. And take note, right? You see, this R and this R are different. Oops, wrong. This R, right, and this R are different. Here we are calculating radius of orbit. Here, this one is for the planet. Okay. Method 2 is just the normal one. Simply just use GM rather than use the GR square. Okay. One thing to note, okay, I will say it one time, later on I'll try not to say it again, is right, you notice gravitation, this topic, right, a lot of indices, or 10 to the power of something. My recommendation to you when you're punching calculator, okay, so in this question, right, how I will do is I will do 3.71 times 3.39 times 3.39 square times 1.03 square times 24 square times 3.6 square, okay, something like that. Then then of course divide by 4 pi square. Then right, times 10 to the power of what plus what plus what, okay, so on. Yeah, so in the calculation, right, it will help if you actually can do some form of your own way, your own style of simplifying things. This is just one style. I'm just telling you, right, this is what I will do. I will calculate all the number, all the coefficient. Then, right, I'll calculate all the indices, right, separately. Because, right, I don't want to times 10 to the power of something, because sometimes you forget to close bracket, open bracket, right, end up you calculate wrong thing. Okay. And in fact, right, this method is very good in MCQ. You know why? Because MCQ, right, if your 4 choices or all your answers are different, all the choices, the value, right, of the coefficient are all different, right, it's only the and that is enough, right, for you to determine which is the correct answer, right? Then you just need to calculate the coefficient, or you don't need to worry about the power, because, right, if all the choices have different coefficient, once you know coefficient, you know the answer. Okay. Pause first. Any question thus far? If you didn't catch me, right, please interrupt me anytime. Okay. No? I go on. Okay, next up, question 2. Define gravitational field strength. Yeah, so gravitational field strength, like this is just bookwork. Okay, field strength and potential, they are the per unit mass version of force and potential energy. Okay, so in terms of calculation and in terms of understanding, right, you use this similarity, right, will help you. Why? Because, right, force and potential energy are very familiar idea already. Or force and energy, what? Oh, easy. So G field is simply, right, a per unit mass force. Okay, whereas potential is a per unit mass energy. So here is a gravitational force per unit mass, okay, acting on a small mass placed at that point. So 2 things to mention here. Number 1, right, is you must say that it is force per unit mass. You cannot say, right, force on a unit mass. This is wrong. Okay. What is the difference? Because force on a unit mass is a force, is a Newton. Whereas force per unit mass is a Newton per kg. So that's a difference. Okay. So you write on a unit mass or confirm wrong. Next thing, right, it must be on a small mass. Okay, on a small mass. Why a small mass matter? Because, right, you see, why is there a gravitational field? It's because there is a planet, or there may be many planets nearby, and because they are massive, they distort the gravitational field, right? So, or rather they contribute gravitational field. If, right, your test mass, you put a big mass, or you didn't use a small mass, you use any mass other than a small mass, whatever you put there, right, will have changed the gravitational field already. Why not? Because it has mass. So that mass will distort the field. And that's not ideal because, right, you simply want to detect the field without distorting it, okay, in the process of trying to detect it. So you must say a small mass, okay? And small, right, another idea that I want you to clarify with, right, is how versus point. Small versus point. Are they the same? Are they the same?
No.
How are they different?
The small mass still has a mass, but point mass is like a point.
Okay, okay. So point mass have mass or no mass?
No mass.
Point mass, no mass. Oh, then later on we'll have a problem when it comes to the definition of Newton's law of gravitation. That's a good try. Anyone else want to provide your perspective?
Is it point mass can be very big mass?
听不到，听不到，大声一点。
Point mass can be a very big mass.
Point mass can be a very big mass, but what does the word point mean?
Uniform density. I don't know.
大声一点。
Is it like something like uniform density?
Uniform density, not exactly, but somewhat.
Oh.
When you say a point, right, can you measure the size or not?
No.
Like how big is a point in terms of size? Can you measure its width? Can't, right? Why not? Whenever you say point, right, we simply refer to, right, something that exists, right, at one location. It has no size one. So that's what point mean. The purpose of using point, right, the idea of point, right, is to say something is located at a certain dot, okay, and not anywhere else, okay. It can be thought of as just there, okay. So it's a more of a location kind of idea. And why is that important? We'll come to the, it's important later on. Whereas small, right, means numerically small, means very light, means very little mass, okay. So for example, right, two planets can be, they can be thought of as point masses, or when you try to apply Gm1 m2 over r squared, okay, to figure out what's the force of attraction, yeah. So they can be thought of as point masses, but are they small masses? No, they are huge because they are planets, okay. I'm just lost all help you. I'm saying all these, right, to help you revise and also help you clarify some ideas. Let's go on. Calculate the speed of the space probe. This part is straightforward because you got the period and you have the radius. So V equals to R omega. Okay, or 2 pi R over T. If you would like to visualize, right, circumference divided by the time taken to travel that circumference. Okay, so check your answer. 3.3 times 10 to the power of 3. Next, find the mass of Mars. So here, right, once again, is a GMM over R square equals to MR omega square thingy. So always, right, make subject, okay, make unknown the subject before you calculate. Don't go and put your unknown, right, in one side of the equation in the denominator or something, and then later on, right, you have problem one. So always, right, Makes unknown the subject, simplify the equation until it's neat enough, then calculate. Okay, so you have 5.82. The answer, right, the suggested solution have a different value because they have rounding off error. My value is without rounding off error one. So you can refer to this. Okay, next up. So after we have figured out, right, what is the radius of what have we figured out? Oh, we figured out the mass. So now, right, we can go on, right, and figure out what is the radius of the planet since we are given the acceleration due to gravity. Yeah. So G equals to gm over r square. So see, correspondingly, this r, right, is radius of planet. Okay. And this G, right, is G at surface. This where, right, like some of you you're not very well versed yet, right? You see all these things, you get very confused one. They must be corresponding. G at where, then the gm over r square, right? R must be that location or that separation or not anything else. Okay. So yeah, you have this. And this number, right, does it make sense or not? If you know radius of Earth, 6,400, roughly lah, because you see newspaper or you see internet, right? Whenever people put the Earth and the Mars beside Moon, right, it's around half like that, or smaller than Earth. Same order of magnitude. Also, it's 3,000. Okay lah, reasonable. Next part, show escape velocity, right, is certain amount. So and you're given how many marks? You're given where's the marks? Oh, 2 marks. A bit too little. Anyway, so you want to say, right, as a mass escape from Mars surface to infinity. Okay, you want to like state the context. Then, right, the gain in GP equals to the loss in KE. Can you see why so? GPE always increase as you go further and further and further away. It's just like you throw something up into the sky. The separation between the object that you throw into the sky, right, and Earth is increasing. What? That's why GPE increase. This is a trend, right? This thing, right, must be ingrained inside you one. Okay, because, right, you cannot go into a new situation. Then need to look at the formula of GPE to figure out, GPE increase or decrease. When R increase or decrease, cannot one. Because the formula is confusing. Minus GM over R or GMM over R, minus GMM over R. So every time if you need to figure out what happened, you may get confused. So as a rule, GP always increase when something goes further. Yeah. And that correspond to loss in KE. So left hand side, right, I would like you to do always this. KE, right, minus 0. Why? To remember that you are taking the difference, not just, right, one thing only. So those of you who never have the half mv squared minus 0, 0 minus GMM over R, you don't have this 0, right, you will get penalized. You cannot say, right, you cannot say half mv squared equals GM M over R. This is wrong. Okay. This must be preceded, right, by the step whereby you minus 0 because you are taking difference. And you must show, right, that you understood this because, right, this is the GPE at infinity. Why not? And this is the KE at infinity. Then the rest is straightforward, just mathematics. And I told you before, right, in previous lesson, this number, right, you see here is 2SF. Okay. So whenever you want to show a sub number of SF, you show one more SF. So here, right, is you want to show 3 also can. You want to show 4 also can. Must be more than 2SF first. Okay. Then, right, after that, then round off. Why then? Because, right, although this is a show question and the number is already apparent to you, But right, how to convince people that you actually got the correct number? You must show this step and you must show pre-rounded off. Both you show you're confirmed correct already. Okay. I mean, don't take much effort. Okay.
Wait, Mr. Quack, can we just like, cause I memorized the formula for escape velocity, like equals to √2 root gm over r, then I just submit.
Not advisable. Not advisable because right, this is a show question.
Oh, okay.
It's just like right. There are a few things that you will have memorized, right? Good to memorize, but cannot use. Cannot use without proof. Okay. For example, escape speed, right? Equals to square root 2gr. For example, range equals to u square sine 2 theta over g. All this, right, you must prove first. Oh, and by the way, right, you see my substitution, I didn't substitute, I didn't evaluate this step, you see. If you notice, right, I didn't evaluate this step. I, from here, right, get to the next step, via the substitution. Wrong arrow. I got to this via the substitution. Gm equals to square root gr. Got it? You understand why this is so? You see, gm over r square equals to g. Maybe I write one more step lah. Gm over r square at surface, okay, equals to free fall, the acceleration of free fall. So why do I want to use this version, right? It's because 3.7 is given to me, okay, in the question. So it's easier, less things to calculate. You don't want also can, you'll get the same answer. Okay, next question. Oh, by the way, right, I forgot to mention. Why, right? This question, I hope to give you a helicopter view. You see, in the beginning, right, they ask you what is G. G is like the force per unit mass thingy, right? Then later on, right, they ask for what is the radius, which is using the formula G equals to gm over r squared. Later on, right, they ask for escape speed. Escape speed, right, is also equals to square root 2 small gr. So you see the first part, right, the definition and subsequent parts, right, all have a string, right, linking them one, and that is the small g. Okay. In fact, right, if you see back each question, right, you can almost see, right, there's always a trend between the definition question at the front and the subsequent parts that you encounter. Okay, they are not like so arbitrarily independent one. Okay. Next up, and I'll show you this what I meant by that, right, later on through more and more example. So you can see, right, Hwa Chong questions, right, all have this style. Okay, it's not random one. The sector, right, is a very helicopter sector. Some lousy sector, right, will set one on this one, on that one, and that. The question not very well linked. But the Hwa Chong paper usually have this pattern. Next up, right, state Newton's law of gravitation. So every particle attracts every other particle with a force that is. So you see, first line, right, one important thing is you must say attract. Okay. Or you can say it's point mass. You can say particle or point mass. Don't say every mass attract every other mass. because right, that will lead to a problem later on. Next, right, proportional to product of their masses, this part no problem. No need to say directly proportional because there's no such thing as directly proportional one. Proportional means directly already. Only when it's not, then it's inversely. Okay, understand? Don't directly proportional. Okay. Why is it that you must say point and particle, right? It's because simply, right, you want square of the distance between them. This part, right, is unambiguous. Suppose, right, you never say you say every mass and every other mass. Then, right, how do you measure the distance? Distance from where to where? Then it get very complicated. Then you need to mention, right, center of mass, or the square of the distance between their center of mass. Wow, difficult. Then you introduce one more unknown. 什么是 center of mass? So don't. So straight away, right, use particle and point mass. 明白吗? Okay, next up, this part, right, straightforward. People who have done this before, right, will find it is so like routine. FG provide for FC. I so tempted to use shortcut so many times, but I better don't in case, right, you look at my second, third time that I use this and I use shortcut and then you get misled and think that you can use shortcut. So I try to do it properly. Then finally you reach the T equals to 2 pi over square root GMR to the power 1.5. At this part, right, many people will just, right until like that, finish already. No, you must, right, be quite clear that it is because, right, this thing is a constant. That is why, right, T proportional to R to the power of 1.5. And this 3 mark. This 3 mark. Definitely, right, you may want to not miss this out. Okay, next. Calculate the orbital period. You see, I told you before also, right? The nomenclature of the question. Between A and B and C, right, there may be some link. A versus B, got some link. Part 1 versus part 2, right? Is strong link. Understand? So part 1, right, you show that T proportional to R to power 1.5. Then this part is to simply use the identity and then you calculate 1.69 hour. Got it? Okay, next up, you're supposed to find the speed of the satellite. The only thing that's tricky here is a kilometer per hour. And because the previous part, you already calculated a period in hour, right? You may want to think, right, I found a period in hour. So I may not want to go and convert anything to second, okay? So just stick with the period, the time, right, in hour. On top is in km. Then settle already, then you will get km per hour. Got it? Okay, next, right, suggest one modification to the orbit, right, of the Iridium satellite so that you can increase the duration of the time window such that, right, of the station with the satellite. You see, so lengthy, this part, right, so lengthy, right, what station are we talking about? So you may want to refer to the question, right? Question say, you got a research station. Yes, most of you probably never bother one, right? You just simply calculate, right? Never read the question. Research station situated near North Pole. Depend on this system, right, for communication. So the research station is at North Pole. So how do you have the iridium, right, like spend more time above the North Pole sky so that you have contact with the satellite? Okay, is right. I mean, there's many ways lah. I actually don't know what's the real way, right, that people would do. But right, theoretically, right, it is one of the way. Change to an elliptical orbit. Why elliptical orbit will spend more time above the particular part, right? We'll go through it in the following question, okay? But I will just let the answer be like that first. I'll explain why, right? Later on, you'll see why this is so already, okay? So I'll proceed without explaining too much first. Any other answer that you want to check whether correct or not? You want to just say out?
Mr. Quack, can you decrease the orbit radius so then you decrease the speed of the satellite?
Oh, so you are saying, right, radius decrease, speed decrease, so that it will be slower and spend more time in the sky.
Yeah.
Is that so?
Yeah.
But wait a minute. Will this, right, be true? Will radius decrease lead to speed decrease? What formula tells you so?
V equals to R omega.
V equal R omega. Okay. But you must ask, right, will omega change or not? Because, right, this thinking, right, that R decrease, V will decrease, right, is based on assumption that omega somehow, right, don't change, ma. What if omega also change when you decrease R? Then this is not apparent anymore. Yeah. Okay. So whenever you want to make deduction, right, between quantities, right, you must check, right, everything got change or no change, and that is a system of thinking. Okay. So if you very confirm, right, this thing never changed, then you can go to a certain conclusion. No, if you unsure, right, then you need to go on and account. Why this thing is constant, like you say, or not constant, like you say. Yeah. But anyway, right, the long and short, I don't want to say the answer. Anyone want to provide a correction to this?
Mr. Quack, I say the opposite. I say increase the orbital radius so that the period will increase.
Okay, so to increase R so that T increase. Okay, this one is a possible one. This one is possible. But actually, right, this one increase the time, no doubt, but it also increase the time that this thing don't appear above your sky. So I think this answer is inside the suggested solution, but I didn't include it because I'm greedy. I want a stronger answer. Yeah, but for most of you, right, if you can say this version, right, this is okay. And why so? Is because back to the equation again. You see, actually, right, I should teach the answer instead. Or I shouldn't teach the elliptical thing. Because, right, I want to teach you that this whole question is linked one. Here tell you T proportional to R. So later on, right, they tell you, right, how do you let it spend more time in the sky? Then you will go back to T proportional to R, have a bigger R. Yeah. Okay. And anyway, right, let me quickly clarify this part. Okay. This part, right, is incorrect. The first one, right, this one is incorrect. Because, right, you know that for circular motion, Gm over 2R, this is equal to Ke. So when R increase, right, when R decrease, Ke actually increase. So speed actually increase. So it will sweep past the sky, right, even faster, or you'll spend even shorter time. Yeah, the arc, right, when you have a smaller r, the arcs, the size of the arc decrease, or that is spent in your part of the sky, then right, it move faster. So you'll end up with a shorter time. And you actually don't need to use that to say. You can simply say, right, r increase or r decrease, so period will decrease. So it will be a shorter time. Okay. Wow, I'm standing beside the window, right? But I'm so hot because I cannot open the window. The wind, right, is blowing and will cause the microphone sound to become unclear. Okay, next part, next question. Okay. This question, right, asks us to derive expression for KE of the satellite. So this part is easy peasy. If you have done it before, it's like a giveaway marks. If you feel that this part is challenging, okay, before this, it means that, right, you're really not well rehearsed enough. Okay, your book work not enough. But after today, you'll be fine. Okay, so the next time you see this is easy peasy already. So I must tell you, right, what are the really easy peasy stuff in gravitation? And in fact, right, those of you who have done it and you hear all this explanation, you start to have a lot more confidence in this topic. It's actually not tough at all. As with most topics. Okay, as with most topics. Some topics are slightly tougher, but gravitation, right, is actually not. It is mechanics, but have some new addition, right, to this picture of mechanics that you have seen thus far. So anyway, GMM over R square equals to MV square over R. So it's the right hand side. MV square over R, right? MV square, familiarly, half MV square. So the R you bring over, and then you times a half, okay, to both sides. Then you get half MV square, so you get a KE. Hence, show total energy. So, and this is a show, remember, so you must make sure, right, that you say things properly. Don't be too quick. So GPE is equals to what? Write down the formula. You don't have to write down at the start, but you can somehow write. Just make sure that your working is not unclear, or why suddenly appear, or you're trying to smoke. So total energy is KE plus GPE. So you add up these two together, you get the minus GMM over 2R. It's shown. Or the next part, okay. So you see, number parts are related. So previous number part is talking about what? Total energy. Formula already given. Why we structure the question like this, right? Why we ask you to show ET is because we are trying to help you. Why then? Because, right, even if you cannot show, you lose the part 2 marks, you can still use the answer to do part 3. Okay, but some people, right, they don't know the architecture of a paper of this question. They don't know that 2 and 3 are highly related. So they also don't know, right, that you can just use, you want to use what in this part. You also don't know. So, but if you understand, right, then you'll know, okay, I can use the total energy. So what's the minimum energy needed? Here, right, it must be implied to you already, that when the satellite goes further, it has more total energy. You can also imply it with the formula here. I forgot to say one thing. I just be slow and help people revise. Also, pardon me, right, if you find that I'm going too long-winded. Okay, so you see all the 3 graphs, right? GPE, KE, all these, right, are the shape of 1 over R. Okay, so KE is like that. And the total energy, right, is mirror image. And GPE, right, is double of the value. Yeah. And pay attention to here, right? This dotted part, don't draw. This don't draw. I draw is to show you, right, that this is a 1/r graph, but right, there is no asymptote or no vertical asymptote because it is truncated at the surface of the planet. So this part don't draw. So here you must like that one. And what's the meaning? Let me ask you. This part, right, is not asymptote, correct or not? Where my pen is pointing. If it's not asymptote, right, then you will have a gradient. You have a gradient, which is like that. What is the significance of this gradient? Gradient of the tangent to the GPE graph at the surface. Any clue? It's actually in I think the next question. Any clue? Recall? Okay. Yeah. The gradient of a potential energy graph is a force. The gradient of a potential against R graph is a field strength. Okay. So this is a force. So this is equals to Fg. Or rather, right, the magnitude of this, magnitude of Fg. Okay. And that is why, right, this part must have a finite gradient. Okay, it must have a finite gradient, not vertical. So, yeah, because this is the only chance that I get to say this total energy thingy. That's why I'm going to say a bit more. And let me remind you again, all these formula, right, only apply for satellite in orbit. Don't anyhow use. When you have something, right, want to go from where to where, right, you don't use this formula one. You don't go and use a total energy formula. This formula come from where? Come from our original definition, Fg equals Fc. And this one is for what? Circular motion. Okay. And the ET, right, is to describe total energy of something in circular motion due to gravitational pull. Okay. So back to here, right, the total energy must be greater at a higher radius, okay, which is the graveyard radius. So you take the graveyard radius total energy minus the Yamal one, okay. Here, right, I want to point to you, right, this thing here. How do we calculate such that, right, it's elegant and won't make mistake, okay. Just now I mentioned, right, you calculate the indices together. That's one thing that you need to take note of, a skill. Here, right, is when you have a 1/r and a 1/r, right, minus another 1/r, you take out all the term, then you leave only the 1/r. And better still, right, you even take out the 1/10⁷. You see what I'm doing here? Such that, right, inside is a very easy number. You press calculator, confirm won't make mistake one. Because if you put the power inside, some of you kanchiong already, right, in exam, you'll make mistake. So this is the most elegant. You punch calculator based on this. Yeah. And then power combined with power, indices with indices. Okay. Have a coefficient with coefficient. Let's get 6.23 times 10⁷. Okay. Next. Here, right, you are given this diagram, not drawn to scale. Monia orbit. Just now is Yamal. Now it's Monia. Russian word, Russian word. Oh, Russian word, right? What can you tell me? In Russia, right? Oh, what is the most common occupation? Anyone? What's the most common occupation in Russia? Nobody know? Oh, it's driver. Oh, driver. Why? Because many of their name is something ski. Translate to Chinese, right, is 司机, or the SKI or SKY, their name 司机. Romansky, Romansky. And Russian people, right, another joke, Russian people always think that they are very strong-willed. Actually, right, they are very weak-minded. Why? Because, right, many of them their name end with OV or NOV, North, Romanov, Petronov, whatever, right? In Chinese, it's called 懦夫. So Russia is full of 司机 and 懦夫. Just a joke. I hope some Russian is not inside our Zoom channel. Okay, this Monia, right, is like that. North Pole is here. Okay, so the elliptical orbit is like that. First up, right, the question asks us to explain, right, why is it that going from P to Q is speed slow down? Okay, so we recall this question start from what? Start from talking about total energy, right? And total energy equals to GPE plus KE, the idea. So to explain why it slowed down, right, is to explain why is KE decrease. To explain why is KE decrease, right, you can just go back the logic link. Oh, could it be to do with total energy and GPE? And total energy usually don't change, because you could never go and disturb the satellite. You're just allowing it to move around, or you never do work during the motion. So total energy remain constant. So what must happen? GPE must have changed. How will GPE change? Well, as you move from P to Q, the separation, right, the distance to the center of Earth is like increase. Q is further, so GPE increase. And this is why I say, right, the idea of GPE always increase with R, right, must be ingrained in your head. You cannot go look at the formula, like that. Okay, no. You see, P is nearer, Q is further, GPE increase. Straightforward one. Okay. Then total energy remain constant, so KE must have decreased, and so will the speed. So it's actually very easy. If you actually, right, catch the clue given by the question thus far, the whole question talking about the total energy, GPE, KE. Yeah. Finally, right, ask you about the advantage. This question, right, if I see this question coming out in exam hall, what to do? Skip. Okay, don't do. Very hard. This kind of ask state of advantage, but I will tell you, right, how to think actually can guess one. You see, this question talking about who? Russia. Okay, where is Russia? Those of you who don't know where is Russia, right? You're hopeless already. Russia is like don't know, is it 1/5 of our land mass? Okay, around there lah. Russia is like everywhere of the northern Eurasian continent. So Russia is like this. Okay, and why is it that, and on the other side as well? Yeah, Russia is from Europe to Japan. Okay, all is Russia. So why is this good? Because, right, this thing to serve who? Russia launched satellite to serve Africa. To serve Africa. Do CIP. No what? Russia launch satellite is to serve Russia. And why you launch satellite for? Satellite, right, got purpose one to beam down signal or you beam up signal to the satellite, then it help you beam to another place or so on. So satellite's job, right, is to remain in sight to your Earth station so that you can play with the satellite. Okay, yeah, that's its use. So in order to play with satellite, you must have line of sight with the satellite. You want the satellite to be above you. And why is this good? It's because, right, this one will, or rather we think logically. So what would be a good satellite? What would be a property of a good satellite? One of that property, right, would be this satellite is above us for most of its period. Whatever the period, maybe if 70% can be inside with the Earth station, very good. Or if only 20%, then you 70%, 80% of the time behind in your shadow, right? No use one. So this one, right, is good because, right, you see, we say that here, right, is slower. Yet, right, further. So this arc here, right, is a huge arc. So you see, this satellite, right, is the nature is as it goes towards the further part, right, the bigger part of the ellipse, right, it gets slower. And yet, right, the bigger part of the ellipse, right, more distance to cover. So if you move slower and more distance to cover, what will happen? You spend a long time. Okay, you spend a long time. So this is actually, right, what this advantage is about. Yeah. So it spent a great proportion of its orbital period above northern hemisphere, where Russia is located. So elegant. But most people will find this hard. I think it's hard also. Okay. And in fact, right, for those people who are interested, I will just share with you this Kepler Law. Let's look from the top view. Ellipse, right, usually is this shape. And the planet usually is here one. This is the planet. There's a Kepler, don't know what law, I forgot already. Okay. This Kepler law, right, is saying that you see, as a satellite, right, move from one point to another point, right, it will have sweep a certain area, this area. And this area, right, is a sectorial area. Yeah. So this Kepler law, right, is saying that the rate of sweeping or covering the sectorial area is constant. Okay, means what? Means, right, the rate at which you cover the area is constant. So if you have a small radius, right, then the satellite must have moved very fast. Okay, versus, right, let's see the other side. On the other side, right, where the radius is very big, let me draw it to be more reasonable. Okay, so you see, one side, right, have a small radius, then you will have a big angle covered in a certain fixed time, such that, right, that gives you the rate of sweeping of the area. Then on the other side, right, you have a large radius, so it must have a small angle, so that the area swept in the same fixed time will be the same as the other side. Okay, so they will have swept the same area in both instances. Or in other words, right, this rate is a constant rate. So if you understand this, right, actually you don't need to understand this. It's just for fun. If you understand this, you can also see, right, how the idea that the northern hemisphere, right, this period of time, right, is the longest one. Okay.
Mr. Quek.
Oh yeah.
Can you explain again in the part I why the total energy is constant?
oh, why the total energy is constant? You actually don't need to say the why, but you can just say, right, while total energy remains constant.
But
Why it remain constant? It is a reasonable assumption, right, that you don't need to explain. But it is because, right, number one, right, what's the basis of the assumption? There's no resistive force in this satellite, in this orbit. That's number one. And there's no work done by, say, the satellite's engine or the thruster. It never do any work, or it's just orbiting, right, by nature or by gravity. So nobody do anything to it. No third party go and touch it. So its total energy will remain constant. Yeah.
okay. But then if I'm not very sure if total energy remains constant, then for this question, can I use the formula for kinetic energy to explain? Like since radius increase, Ke decrease.
Cannot. Why?
Oh.
This is a good question. I forgot to say, I forgot to explain why cannot use this one. Okay, you see this question, right, seems to be like our answer, first talk about GP increase, total energy constant. Then we indirectly deduce what happened to the KE, correct or not? KE will have decreased. Why cannot, right, directly go to this formula and say when R increase, KE decrease? Anyone want to make a guess? Why cannot say this? Cannot use this to straight away deduce what happened to the KE?
Because it's not a circular orbit.
Exactly. This come from what? This come from the circular motion derivation. Okay, which is why, right, this question, right, 绕来绕去 talk about is indirectly deducing KE rather than directly using a formula, because there is no applicable formula. Okay, this formula is not applicable for the ellipse. But then you may ask, right, then what about the total energy formula? That one applicable, man? We also don't know what applicable, because, right, whether you see ellipse or circular motion, total energy is always equal to potential plus KE. That one is confirmed one. It is not even restricted to constraint to orbits. Is general. Total energy is always potential energy, all the type plus kinetic energy. Okay. Really thank Clarice for bringing this up. So see, this is very good. Now you all must say. Then sometimes I forget certain point to say. Okay, next one. Okay, here this one you have a asteroid. This asteroid massive, 10 to the power of 18. This one hit Earth, will immediately, right, go and meet dinosaur already. Same fate. Okay. Asteroid, right? A few 100-meter asteroid hit Earth, already city-wide off. Few 100-meter wide asteroid. How big is that? Like a size of a stadium, an asteroid the size of a stadium hit Earth, or a shopping mall hit Earth. One city will be wiped out. So you think a Suntec city fly down from the sky, hit Singapore, whole Singapore wipe out. Minimal minimal. If a kilometers wide satellite, right, hit Earth, then you'll be like a mega city, or like Shanghai, this kind, very huge city wipe out. This 10 to the power of 18 kg. How big? I also don't know. Need to calculate the radius. But this look massive to me. Okay. So calculate the change in GPE. Like I say, right? Remember, take out even the power. So everything, right, is out. So you here only have a simple 1 over R minus 1 over R. Okay. And you should expect some things. Okay, what should you expect? This thing come from high to low, or S is on Earth surface, okay, on planet surface. So this GPE change, right, must be a decrease. Or not? It go from high GPE to low GPE. So the change in GPE must be a decrease. It must be a negative number. So you calculate, end up if you don't have negative number, right, or something wrong. So you need to check this. Okay. Next. Just now they asked what? They asked GPE, right? So let's see. This question here, how does GPE, right, change, be reflected, right, or represented in the graph? Well, is it related one, So just now I already told you, F is equals to minus du dr. How do you say this? Or you say, right, gravitational force is the negative of potential energy gradient. This is a way of saying that equation in words. Okay. We asked this before in exam. We asked what is meant by potential energy gradient. Yeah, that would say it is a negative of the gravitational force. And with this, right, you can see that the flip side is R1 to R2. This one gives you the change in U. Okay, correct or not? One is the differentiation version, one is the integration version. So it's the area bounded by the graph. And R exists between two values of R. So that's what you say. Okay. I think this part not going to be very well done. Some people, even they roughly understand, right, they may not say it clear enough. Next, describe and explain, right, the motion of the satellite as it moves from H to S. Describe and explain. So you need to explain also. This is 2 mark, right? I feel it's a bit too much. Like a lot of things to say. So what happened? So you don't need to describe first, then explain. You can explain and describe also can, as long as you met the objective. So as you move from H to S, what happened to the GPE? GPE decreased, right? So total energy, if it remain constant, then K will increase. So speed will increase. So you see, I've explained and described what happened. Speed increase because GPE decrease. Yeah. So this part is the describe. And this part is the explain. Yeah. Then actually, right, I personally think that this will be enough already. This will be 2 mark. But when I see the suggested solution, right, you also have the description about acceleration. Well, I would think that is actually not necessary because, right, like a bit too much for 2 marks. But since you're given this graph, right, you should also see that as you go closer and closer, right, what happened to the magnitude of the force? Magnitude of the force increases. So this means, right, acceleration increases. So this will mean, right, the velocity, right, the speed will increase at a increasing rate. Okay. So you can also say, right, GPE decrease, total energy increase, total energy constant, so K increase. Moreover, FG increases as well. So speed increases at a increasing rate. So that could be your final verdict, final description. So one line contain both description. So see, this part is this part is explain, and this part is describe again. So you can lump all the explain in front, or the describe in one statement also can. Okay. I pause a while, let you copy if you want to. And meanwhile, you can look at the next part. So what if, right, the planet is also rotating? How will the graph change? Okay. This one, I feel this is also tough. Okay. So the graph, right, you must think of two part of it. Okay. You see, planet rotating or not rotating, right? When you are far away, doesn't matter one, because this graph, right, is a F against R graph. Okay. So let's look at the graph again. This is a F against R graph. It's loading slowly. So F against R, right? This F is what? Is G M1 M2 over R square, okay? Nothing to do with the planet's rotation. Or you rotate lah. You rotate, will change the mass, meh? Won't change the mass, what? Correct not? Or will change the R, meh? Won't change the R, what? So what's the big deal? Okay. So at large distance, right, it's not a big deal at all. Yeah. So the graph, right, will not change at all. You have the same shape. But right, when the separation is small, okay, then right, you see from far you cannot see the planet. It's just a dot. But when you go near, asteroid come nearer, right, then you see, oh, this planet start to appear like a planet. Then right, you need to ask, this sphere, right, is it sorry, this planet, is it spherical or not? If not spherical, right, its center of mass may slightly change position, okay. So will that affect the value of G? It will, because the mass value don't change, but the R value may change. Or what if the planet is lopsided? Lopsided, one side of the planet heavy, one side lighter. Okay. So you want to talk about whether the planet is spherical or density the same or not. Okay. If the density not uniform, planet also not spherical, then right, the graph may change. Okay. Change by much? No, I don't think so. Change slightly. I feel this is tough. Not many people will do this part well. Okay. This will be the last question for today. I think in the past sessions, right, always too long. Say until you tired, your mind also blank out. So I want to end today, right, with you feeling fresh, and all you retain the idea better. Yeah. And then you can apply what you learned today for the remaining question. This question, right, you see this kind of graph, right? Immediately, you don't need to even read the question. You use your hand, touch the exam paper. You feel, oh, got a printed graph, got this kind of graph grid, right? Rough one. You can already predict, right, what is going to come out in this question, if it's on gravitation. It is definitely about this equation, G equals to minus d phi dr. Confirm one. Okay. Whenever you are given a grid, right, for the graph, it will mean that you need to find, number one, either area or more likely gradient. And in what context will we find gradient? Find gradient in the phi against R graph. Okay. Otherwise, right, why don't we give you a vague, generically drawn graph? Why do we give you on a graph paper? Because you need to use the graph paper, right, to figure out features of the graph graphically. Okay, you need to do graphical work. That's why you have the graph, this kind of grid. You understand or not? Okay, so there is a logic. So with that, right, hence determine the value of the force, magnitude of the force. So what is the force? Force usually, right, is simply equals to mg lah. Okay. Oh, then you ask, what about the g? The m is straightforward. Well, the g will be the gradient. Okay, the magnitude of the g will be the magnitude of the gradient. So here, right, I haven't drawn. I will draw it live. Not difficult lah, not difficult. But somehow, right, some people still mess it up. Oh, something like this. Okay. Shift to the right a bit lah. I'm drawing on the tablet. Can't draw too nice. Okay. And take note. You want to use, right, a big triangle. Okay. Use as much of the graph as you can. Doesn't matter if the point is not sui in the corner type, or it can be half a square. Then read off lah. What was difficult about reading to half a square? Yeah. But be very careful, right? In this question, most people make a mistake, right, with the power. Okay, they miss out this power. Then they will get the wrong answer here. And in such case, right, when we mark, we'll record this as a POT error. POT error means what? Power of 10. Okay. So this is a common POT. Whenever you are dealing with graph, make sure you check axis, okay, to avoid POT error. Get a number. I move on. 1.4 Newton. Wow, this one better don't come out. I hate this question. Always come out one. Every time you're asked about gravitational potential, right, or you see those kind of graph, as a package, you'll be always asked why gravitational potential are negative. Okay, it's a package one. Why then? Because this is a good question now. This is just a very good question. So you see, we want to ask ourselves, right? This one is, take it as a revision for all of you. The gravitational potential, right, is work done by external force, okay, in bringing the mass where do I put the per unit? In bringing mass from infinity to that point, okay, without change in KE. Yeah, so this question is saying, like, with reference to the definition, also you definitely need to refer to the definition and explain. Okay, so number 1 point, right, what do you say? Is to say, okay, gravitational force is attractive. And why do you say that? It's so as to allow us, right, to say that, hence, right, the external force in this case, in the context of the definition, right, is acting opposite direction to gravitational force, which is outwards, which is the opposite of attractive. You understand? So first, we say gravitational force is attractive to allow us to clarify that the external force is actually opposite of the gravitational force. And next, right, you're moving from infinity inwards. So you see, your displacement, right, is a inwards displacement. So this will also, right, mean that the external force, right, is opposite direction to this displacement. Okay, and therefore, right, this work is negative. Okay, And since, right, potential at infinity is taken to be 0, then, and with this potential being negative, right? So, sorry, with this work done being negative, right, then the potential will hence be negative. Okay, why then? Because, right, the phi is the work done, and the work done, right, is equals to the potential at infinity minus the potential at that point, yeah. So we must establish, right, that this is 0. And since, right, your work done, right, is all negative work. So 0 coupled with the work done being a negative work means, right, what comes out of it is a negative quantity. Okay. So you have two things, right, that you must establish or not. So it's to establish the 0, the potential is infinity is 0, then establish why the work done with reference to the definition is negative. Combined together, the potential will hence be a negative number. Sorry, let me rewrite this. So the work done equal to the work done per unit mass is equal to the potential at infinity minus the potential at that point. Okay. Yeah. So the potential at that point would be equal to work done per unit mass plus potential at infinity. So you see, we are trying to show that this is already 0 by default, by setting. And then we want to show that this is negative. And how you show this is negative is the huge chunk of words we have in the middle. Okay. Finally, right, determine the minimum speed. You must give the rod so that it can reach the surface of B. Okay. So let's go back to the graph again. You see, this graph, right, is phi against R, but it's no different, right, from U against R, because, right, is simply equals to U divided by mass. Okay, so this can be thought of as a potential energy graph. And this potential energy graph, right, is just like a real hill, like a real landscape hill feature. Okay, so if you want to get to the other side of the hill, right, most important thing is you must have enough KE. Assuming your way of getting to the other side is by rolling, you're a ball. You need to have enough KE to roll to the top of the hill. Someone give you a kick and then you roll up. Okay, and as you roll up, you lose KE. But once you get to the top, right, you don't need to worry already, because, right, the other side, you simply roll down. You don't need to have any KE to roll down. You'll in fact gain KE as you roll down. So you're concerned with, right, how you get up to the top of the hill, how much KE you must have so that you can successfully roll to the top. Thus, right, from this graph, to understand what is the minimum KE needed, right, or minimum speed needed, is to understand, right, what will be the loss in KE. Okay, which is this amount. This amount is a delta phi. This delta phi times mass will give you the delta GPE. Okay. And then you know, right, the delta KE will be equals to the negative of the delta GPE law. Oh, the magnitude is the same lah. Because one is a gain, one is a loss. So that's how you go about solving. And the minimum speed, right, will correspond to the case whereby the top, or when you reach the top of the hill, your KE will be 0. Okay. So that's what you have here. So you need to do some explanation, I feel. Okay. Because whenever people say that this is a minimum speed, right, it is implied that that there's a certain meaning behind it. Okay, so why do you straight away use, right, compare the why do you put a 0 here? Okay, why do you put a 0 here? Oh, this, right, is the significance of the minimum speed, because with the minimum speed, you reach the top, you're just nice have 0. If you have more than the minimum speed at the bottom of the hill, can you go up? Oh, definitely you can, because you already met the minimum criteria. So by the time you reach the top of the hill, you will have a non-zero KE. You haven't used up all your KE yet. So, but the minimum case will correspond to the top of the hill having 0 KE. Yeah, and that's why, right, this side of the equation must be half mv squared minus 0. And once again, right, if you straight away write half mv squared equal m delta phi, right, this one, right, oh, not so good. I wouldn't go. I may deduct a mark lah if I'm the marker, but I will see how the cohort do. If too many people make this mistake, I may not want to deduct the mark then. Okay, but I will prefer, right, that you show half mv squared minus 0. Okay, so check the answer. Finally, right, question asked, suppose, right, a rock has a speed that's greater than what you calculated at the initial launch point. Without further calculation, okay, sketch variation with the KE with the distance. Well, this one, right, you see, if, right, you only have the minimum KE, then your graph, right, will be just the mirror image of the potential graph lah. You'll be like this. Oh, when you reach the top, you'll be 0, and then, right, you'll roll down the hill, roll. The other side, right, will be higher than this side. Okay, but that is if this is the minimum speed case. Now you have more than the minimum speed case, so it's apparent that the answer will be 1, whereby it's just higher by a fixed amount. So here is still a certain value that you start. There you must end higher. Okay, and here, right, you will still have a turning point at 0.54, and you sketch it. Okay. And I put a note here. The question could be asking for speed as well. And you may think that, hey, KE is KE ma, is half mv squared. What about for the speed? Well, this is a curve. You don't know how to square root a curve, right? But you don't need also same shape. Because when you square root a curve, you'll still get back a curve. And what's important is here lower than here, and here is a minimum. Oh, forgot to label. Here you need to label the 1.0. Is it 1.0? What's on the graph? Oh, no, 1.2. Okay. Any question thus far? Do you feel your gravitation now starting to reach quite a high level already, that you are not so scared anymore? Or still scared? Or humble? Oh, we shall see lah, in your promo. I think no problem. After you do all this, right, you will have seen so many type of question. Also don't need to be overly extensive, but enough types, right, to help you appreciate. Okay. And why coming to this kind of session, right, is important because, right, you can read the answer. Answer only tell you what to do. Answer wouldn't give you a helicopter view of the question. Answer wouldn't help you think from the point of view of a setter. Because, right, once you have the point of view of a setter, right, you have the 上帝视角, okay? 上帝视角 is what? The God view. Once you have the God view, right, you're invincible already, okay? The only thing that may screw you up is press calculator, press wrongly. Understand? So I think all of you, if you have understood today's lesson, you are quite invincible. Okay, any last questions before we end? Shall we finish up the rest of gravitation, right? Perhaps on Friday? Possible?
Yes, Mr. Greg.
We try Friday lah. It wouldn't be long. Friday I will go faster already. Today we covered quite a lot of ground. Then, right, the mechanics one, I will give you a few days. Friday. I try to upload it by tomorrow. Okay, the mechanics. Then hopefully, right, Sunday we can have another quick one. Sunday we'll do some circular motion. Circular motion I will give you Kepler already. Because circular motion, the easy question, right? You'll get bored one. But the Kepler ones, right, are really quite Kepler. Okay, so we'll do some Kepler one. Not going to be long. Then the following week, right, will be mix. Okay, mix of various topics coming together. Because a lot of times, right, very hard to segregate out. Those questions that you can segregate out nicely, usually not very difficult. A good mechanic problem, right, usually everything lumped together. Okay, and you need to switch your angle of thinking, right, from force to energy, energy to force to motion. Okay, then that way, right, it can't be very well segregated into by topic. Yeah, that's what I meant by why I say we have a mixed mechanics section. And in fact, right, I feel okay, my personal feel is, while gravitation sounds daunting, mechanics, right, is the only one that could be potentially difficult. You understand what I'm saying? Superposition, right, because you are new, the question bound to be easy one. I can guarantee you. Where the teachers will be more cautious, right? When trying to assess you, they don't want to test something too difficult when they are testing it the first time. What topics have you been tested multiple times? Mechanics. And you're always what you think your mechanics very strong. People always underestimate. That's why it got the potential. Topics, right, whereby the more complex it sounds, the narrower, right, the way it can be tested. Okay, like diffraction grating. The first time you hear it, what is diffraction grating? And then you look at the diagram, it looks chim, right? But later on you realize, right, there's only one thing that you need to know. D sine theta equals to n lambda. Super easy. Okay. Next year when you do quantum physics, right, you realize quantum physics is super easy again, because actually I should generally it's A level is easy. Why? Because it's high level. But high level things, right? A lot of things you don't need to know one, not expected. So the things that you can only be tested are simple. Whereas mechanics, right, is basic, but can be difficult. Yeah. Okay, have a great day and a great dinner. I'm going to cook already. I talk too much. Oh, I want to end early is also because I want to cook. Okay. Oh, so see you.
Thank you, Mr.
Thank
Quek.
you, Mr.
Quek.
Quek.
Bye bye.
Yeah, Mr. Quek.